Ultimate Transmissions have developed an advanced variation of an already very successful CVT mechanism, the Toroidal Variator. The normal single rollers are replaced with a double roller. The result is a much simpler, smaller, lighter, cheaper, more durable and more efficient transmission. The full Toroidal Variator is best known by the brand name Torotrak. A drive shaft carries power from a rotating power source into and through the mechanism. The shaft includes oil galleries that carry high pressure oil to the clamping system. A clamping plate is fixed to this shaft and acts as a combined hydraulic clamp and hydrostatic bearing supporting the output disc. It is fixed to the shaft both axially and radially. The output disc bears up against seals that are embedded in the clamping plate. These seals form a hydrostatic bearing located in its underside, between it and the output disc. The output disc is free to rotate on the shaft, supported on needle bearings, and is not connected to it. The input disc is located at the far end of the shaft and is fixed to it, both radially and axially, using a simple screw thread and locking nut. When the input shaft is rotated, both the input disc and the clamping plate rotate at the same speed. The output disc will not rotate until the rollers are clamped between it and the input disc. The rollers are arranged in pairs within the toroidal cavity. They are clamped between the input and output disc by high pressure oil supplied to the hydrostatic bearing under the clamping plate. The rollers are machined with both toroidal surfaces and conical surfaces. The toroidal surfaces roll on the toroidal discs, while the conical surfaces roll on each other. The centre line of the conical contact passes through the intersection of the roller's rotational axes. The tangents of the toroidal contacts coincide with the intersection of the roller axes and the disc's axis of rotation. This arrangement eliminates any differential velocity at the contacts common to single roller full toroidal variators, like the design adopted by Torotrak. In this position, the double roller CVT is almost 100% efficient. It can also be seen that when the roller pair is in the central or 1:1 ratio position, everything rotates in the same direction and at the same speed. At other ratios, the relative speeds are different, but the direction is always the same. With a single roller arrangement, the discs run in different directions all the time, continuously wasting considerable energy. When the rollers are in the 1:1 ratio position, they contact the discs at the same radial distance from the disc's centre of rotation. Consequently, in this position, the input and output speeds are the same. When the rollers are steered so that they contact the input disc closer to its axis of rotation and the output disc further away from this axis, the CVT moves to a low gear position, with the output moving slower than the input. When the rollers are steered so that they contact the input disc further away from its axis of rotation and the output disc is contacted closer, the CVT moves to a high gear position, with the output moving faster than the input. The ratio of the small to the large radius determines the overall ratio spread. This can be as high as 6:1, as with other forms of the full toroidal variator. In both high and low gear positions, the CVT efficiency falls to around 97%, as there are now small differential velocities at the contact points of the rollers and the discs. Some energy is also lost in the hydrostatic clamping bearing. However, the average mechanical efficiency of the CVT across a range of ratios will always remain well above 98%. The matching of the surface contact speeds, not possible with other single roller designs, also produces an extremely high power to weight ratio. For the same power throughput and greater efficiency, the double roller design is less than 1/3 the size of a typical Torotrak single roller variator. The matching rotation directions and low differential contact speeds also make the double roller design more durable than others. The simplicity associated with the matching rotational directions reduces the high parts count common to single roller designs, which must use a double cavity. The small size and low parts count make the double roller design much cheaper than others. The double roller full toroidal variator can deliver a smaller, lighter, more efficient, more durable, more versatile transmission, containing fewer parts and at a lower cost than any other form of automated transmission.